Welcome to the last talk of the day. I hope I can keep you engaged for 20 more minutes. So who am I? I'm Yashwant. I work at NVIDIA. I work with the CPU compiler team. We try to contribute to the R64 backend in upstream LLVM. And for past year or so, I've been working with Numba as well, and Numba is a LLVM-based JIT compiler for Python. I have a few slides about Numba as well upcoming. Okay, starting off with what exactly are llvmlite and Numba. So Numba is an LLVM-based JIT compiler for Python. It is used widely to speed up your Python code by a factor of 100x to even 1000x. And the way it works is, so Python is an interpreted language, and Numba tries to bypass the Python interpreter, and instead of relying on the interpreter, it JIT executes the Python code using LLVM's JIT execution engine. So it lowers Python to LLVM IR, optimizes it, and then executes it on the machine. And LLVMlite is the bridge that connects Numba Python frontend to LLVM's backend. And this talk is going to focus more on LLVMlite. Numba in itself is a very interesting topic, but there are a lot of resources available about it, and you can read more about it. But I'll still give a brief overview of what exactly Numba is. So Numba, as I said, is a LLVM-based JIT compiler for Python. The way it works is you start with Python, which is then lowered to something called Numba IR, which is very close to Python, but I haven't exactly worked on Numba IR, but then Numba IR is then lowered to LLVM IR. Once you have the LLVM IR, it is then optimized using LLVM C++ APIs, for which we have wrappers and LLVMlite. One more thing, the Python to Numba IR translation to LLVM IR translation is again done by LLVMlite, which acts like a compiler frontend for Python. Once you have the optimized IR, you can just generate the machine code and directly execute it on the machine. So here I have an example which demonstrates how you can use Numba to speed up your Python code. So I have two functions which calculates the sum of a NumPy array. However, in the first function I am decorating it with a JIT decorator, which instructs Numba to JIT compile this function instead of invoking the Python interpreter. And if you see at the execution speed, you can see the JIT executed function is a lot faster than the normal Python interpreted function. So it's around 60.1 microsecond compared to 5.14 milliseconds. Coming back to this talk, I'm going to talk more about LLVMlite, and basically three main things in LLVMlite which makes LLVMlite what it is. The IR builder, which is a compiler frontend, and LLVM playground. I'm calling it LLVM playground. I'll show you some examples how you can use LLVMlite to develop day-to-day tools as a compiler engineer. And in the very end, I have a few slides about how you can directly execute any LLVM IR you have using LLVM's JIT execution engine in Python. So disclaimer, so some of the examples in these slides might not work. The reason is there are some pull requests that are still waiting to be merged, but you have them and you merge that pull request locally and build LLVMlite, everything should work fine. And I've tried to push all the code examples in the second link. This is the Python notebook, which contains all the examples that I'm going to go over today. Starting with IR Builder. So IR Builder acts as a compiler frontend, which allows you to lower any programming language to LLVM IR. And in this talk, I'm not going to show you how to build your own programming language. I'm going to focus on few examples on how LLVMlite IR Builder works to generate an LLVM IR function. So let's try to build an LLVM function with adds two integers, a very simple function. Let's see how we can do it. First things first, we'll import the IR layer for LLVMlite. It contains all the APIs for building the LLVM IR. We'll create an empty module, we'll name it my module, and then we'll define the function. In the first line, I have tried to define the function type. So the first parameter is the return type, which is an integer of type 32. And then I have a list of parameters, which are the function arguments, again, two parameters of type 32. And I have added this function foo to the module mod, and I have named this function add2. Once we have done that, we'll try to add some basic blocks to our function. Since this is our first basic block, let's call it entry. This is how you do it in LLVM. And so this IR builder acts as a pointer to the LLVM IR that you are building. It works at 3 layers of abstraction. So builder.block will point to the basic block level. It's helpful for adding instruction at basic block level and things like that. Then you have builder.function, which is a slightly higher level of abstraction. It is for modifying the IR at the function level, the function return type, arguments, and stuff like that. And then you have the highest level of abstraction, builder.module, which you can use to modify module-wide changes such as module name, target triple, data layout, etc. Let's try to add the actual instruction in our function. We'll capture the function arguments in A and B, Python variables A and B. And this is how you add an add instruction to the function. Builder.add, which takes two parameters A and B, which are the function arguments that we have captured in Python variables A and B. And we are calling the output variable C. And let's add a return instruction, which returns this variable C. This is the final code. It's just the same code in one slide. And this is the output IR. So we have the module name set to my module. Target triple is unknown because we haven't set it yet. Target data layout is empty, but the function return type is i32. It has two parameters of type i32. The name is add2. It has one basic block called entry, and it has two instructions, an add instruction and a return instruction. The output of add is in a variable C, and we are returning that variable C here. You don't have to stop there. Numba actually does a lot more than just building the basic LLVM IR. It's a full-fledged compiler. You can try. Let's try to do something. Here I have tried to rename the function module to test module. I have set the target triple to arg64. You can even add function attributes to the functions in the module. Here I have tried to add the no inline attribute. Let's try to see how our module looks right now. So you have this no inline attribute set now. The module name is seen, and you have target triple set. All right. As you know, LLVM IR module can contain a lot more functions, not just single function. Let's try to add another function to a module, and this time this function takes 3 parameters, and it will return the sum of those 3 values. So I'm not going to go over the code line by line. I'll give you a second to just get an idea about the code, and we'll just go over the output. Yeah, so as you can see, now we have 2 functions in a module. This add2 is the older function, and now we have add3 function as well, which takes 3 parameters of type i32 and returns their sum. We have 2 add instruction, which we added over here, the add1 and add2, and then we have return instruction, which we added over here. Moving on, coming to the second part of the talk. So I'm going to go over a few examples, which will show how you can use LLVMlite in your day-to-day compiler workflow if you are working with LLVM directly, and find C++ a bit intimidating for rapid prototyping with LLVM. So let's try running some of the LLVM's optimization passes directly. So we are going to try to run a pass on this LLVM IR. So this time we are not building LLVM IR on our own. Instead, we are parsing the LLVM IR from Python string. So we have a Python string over here, which is an LLVM IR function, and this is how you parse an LLVM IR module, a Python string to a LLVMlite module object. If you notice here, instead of importing the IR layer, we are importing the binding layer, which contains the APIs which interact with the LLVM itself. Once you have the module object ready, we can start with our experimentations. First things first, we are going to do some initializations. This will initialize the native target in the assembly printer for the machine you are working on. We'll define some helper functions. This target machine function will create a target machine object for the machine you are working on. Again, pass builder. Pass builder is a class in LLVM which is responsible for managing the analysis and the automation passes under the new pass manager infrastructure. This is just a Python wrapper over that C++ class. Then we have an npm function will return a empty module pass manager object. We'll use it to run individual passes on a Python on an LLVM IR module. Okay, let's try to run simplify CFG pass on this IR. So this is how you do it. First, you create a pass manager object using the npm function we defined in the last slide. You create a pass builder object. You add and simplify CFG pass to a pass manager object, and you just call the run function on it. And that's it. This is the output. We don't have to go into the details of the LLVM IR. You can see here we have, that's how many? 1, 2, 3, 4, 5 basic blocks. Here we have 3 basic blocks. The input is significantly different than the output is significantly different than the input. How about default automation pipelines? So you are not limited to individual passes. You can run the default pipelines O0, O1, O2, O3, etc. You don't have to stop there. You can combine those pipelines with your custom optimizations. You can sandwich multiple optimization pipelines. You can do basically everything. you can think of with LLVM passes. So here I've tried to run O3, we'll try to run O3 pipeline on this LLVM IR module. Again, we'll create a module object from the Python string. We'll parse it into a module object. Let's create a pass builder object. This time we are creating pass builder object with speed level 3. Speed level 3 will correspond to O3 in LLVM. Okay. We'll query the pass builder object to give us a pass manager object. What this will do, it will return us a pass manager object with all the passes initialized for O3 optimization level. We'll call the run function on it, and this is the output. As you can see, the output is significantly different than the input. This was the O3 pipeline. Moving on. So this is my favorite part. So LLVM has a plethora of visualization passes that you can use either for debugging or just trying to figure out what exactly is going on with the optimization. LLVM has passes that visualize control flow graphs, dominator trees, post-dominator trees. It has variation of those passes that can print those graphs with less verbosity. So we'll try to create some quick functions in llvmlite to easily access these passes. So here I've tried to define a Python function which will generate a control flow graph of LLVM IR module. Going over the code, I'm creating a pass manager object in the first line, then I'm adding a CFG printer pass to it, and I'm calling the run function on the module that I'm passing the parameter. And in the last line, I'm converting that. So that LLVM pass basically generates a dot file. In the last line, I'm converting the dot file into a PNG image, and I'm naming the image as the second parameter that I'm passing to the function. How do we call it? This is how you call it. We call the render modulus.graph function with this count zeros module. This is the module I have defined in the left, and I'm going to call the output file count zeros. Let's see the output file. This is the output image. Come on. Okay. So again, this is not something new. LLVM already does it. I'm just trying to showcase a new interface to do the same things that you have always done in LLVM. Okay. So more visualizations. So you don't have, I think I have a few more examples. Yeah, this is generate DOM tree function. It will generate the dominator tree of a LLVM module. Then I have a generate post DOM function. It will generate a post dominator tree of the LLVM module. Building custom optimization pipelines. Like I said before, you can build your own custom optimization pipelines using llvmlite. So let's try to do some experiment with this LLVM IR module. So first things first, we'll create a module object from this Python string. And here I've tried to create a very random pass pipeline. So I was not thinking about doing some kind of optimization over here. I just wrote whatever passes I could find in llvmlite and arranged them over here. This is just to show you a glimpse about how you can create your own custom pass pipelines in it. You can club these optimizations with default optimization levels such as O1 and O2 as well. This will come particularly handy when you are working on, let's say, some optimizations, for example, some vectorization, and you want to test its effects on how does your optimization works with some of the loop optimizations. And you also want to quickly test what happens if I reorder those optimizations. So you can quickly come up with a Python script, define some functions, and basically automate everything and just look over the outputs. It's great for building fuzzing tools and debugging tools. Yeah. So this is in the last line, I'm calling the run function on this module. This is the output. Something has happened to the input because of these passes that we had earlier. How about code gen? We can also look at the assembly. So here, instead of initializing native targets, I'm trying to initialize all targets because I want to show you assembly for multiple targets. Spoiler alert, you need LLVM built for all targets, otherwise it won't work. It will give you some error, something like target triple not recognized or something. So here I'm trying to create a RISC-V target machine from a RISC-V triple. Then I've created a x86 target machine from a x86 triple, and I'm creating a native target machine from a default target. This will be the target machine for the target you are working on. It will automatically query the triple and create a target machine. Spoiler alert, this is, I was working on an ARC64 machine, so this native target machine is an ARC64 machine. We'll try to generate assembly for this LLVM IR module. So I'm going to skip over the part where we try to optimize LLVM IR because we already know how to do that. Instead, I'm going to show you how to, we'll just look at the assembly output for this unoptimized LLVM IR. So it's very simple. You just call the emit assembly function on the target machine object and you pass the module you want to look the assembly for. So in order, we have x86, RISC-V, and native, that is ARC64 assembly. It's not very readable, but you can take my word on it. These are all different assemblies. Okay, coming to the last part, executing your IR. So let's try to execute the add2 function that we created in the very first slide. Yeah, so instead of using the module object we created earlier, I'm gonna create a module object, a fresh module object from a Python string, just to keep the slides contained and for simplicity purposes. We could have reused the same module object, but I'm creating a new module object from this Python string. I'll parse it into LLMod. Once I have it, I'll create a target machine object and I'll create a compiler object. So this LLVM.create mcjet compiler, this will create a mcjet compiler instance that we have in LLVM. So LLVM has two JIT execution engines, mcjet and awkjet. llvmlite is currently relying on mcjet. But you feel free to propose a change to shift to awkjet. It's actually one of the ongoing projects that nobody has picked up yet, but it's definitely something if you want to contribute to llvmlite and Numba environment. So, and compiler.finalize object will create the binaries or the machine code for this LLVM IR. Once you have it, you can execute that function using function pointers. We'll query the address of this add2 functions. Once we have it, I have to execute it with two sets of input, -1 and 2, 1 and 2. You'll get the sum 1 and 3 respectively. Yeah, thank you so much for listening. If you have any questions, I can take them now.
Hey, thank you. Maybe your slide 54, I think, where you showed the pass pipelines. Do we have the facility to pass, let's say if I have, pass has like multiple options, can this facilitate feeding those options as well? Let's say the threshold that you show on the inlining side, it's just one there, but if there are multiple options for a complex pass, then can we feed them all through this?
So there are two things over here. First, you need a wrapper around the pass you want to experiment in. So let's say, so some of these paths I have commented out are yet not supported in llvmlite. It's very easy to support them. It's 10-15 lines of change. So once you have that support, you can call that pass. Then the other thing is you should support the passes with particular parameters it works with.
Yeah.
So here inlining threshold has a inlining threshold parameter which defaults to 25. Which you can override.
Yes. Okay. Thank you.
So my question is, is there any support for allowing us to write our passes or rewrites in Python itself? Because now you're just calling passes that already exist on the C++ side, right?
Yeah. You should be able to do that. Nobody can stop you. You can write your own passes in Python. But the downside will be you won't be able to use the data structure that we have in LLVM that allow you to easily write optimization passes.
Okay. So I know from the MLIR side of things, or the Python bindings, they actually have an issue with allowing people to write rewrites in Python, basically because there's an ownership mismatch of the memory of the different ops. So when you start manipulating ops on the Python side, C++ thinks about ownership differently, and now there are issues. Do you think this is also the case on the LLVM side or not?
I'm not aware of it, mainly because llvmlite doesn't have custom passes right now. So maybe that's why they haven't done it. llvmlite basically exists to cater to Numba. So whatever Numba needs, they support it. Right now, Numba doesn't need a custom pass, so they don't have that functionality. But it's still an individual project. So if somebody wants to write custom passes in it, want to use more LLVM interface, they can either create their own fork or contribute to llvmlite and expose more LLVM data structures and APIs in llvmlite. or even write their own passes. But this memory safety issue, I'm not aware of it. It sounds interesting. Maybe we can chat offline.
Thank you.
Yeah, sure.
Thank you for the talk. I wanted to ask how exactly you are binding to LLVM, and is it easy to use a custom LLVM build? So, for example, if I don't know, change something in the code gen, can I use llvmlite to use my LLVM build and play around with it?
So for the first half of your question, LLVMlite uses C types to interact with C++ code base. It's a standard. It's not very difficult to use. If you look at the code, it will be very intuitive. I didn't get the second part. Can you repeat the question again?
I mean, if I create a custom LLVM build with some changes of my own, can I... but I guess the answer is yes, because you said it uses C types, so then I can use my own LLVM builds.
Yeah, you can. For the slide examples here, I'm not actually using the upstream LLVMlite, and I'm using LLVMlite with my own build of LLVM. Upstream LLVMlite still stuck on LLVM 16. We are trying to move it to tip of trunk. There are pull requests open for it, like I mentioned earlier. So yeah, you can do it. I'm basically doing it in my example. There is an environment variable that you can use to point LLVMlite to your build of LLVM, and we'll try to interact with those LLVM APIs.
Okay, thank you.
Sure.
Hi, thanks for the talk. My question kind of has two folds to it. What do you see like the use case of LLVMlite is, maybe opposed to, let's say, MLIR Python bindings? And maybe the second question is, what does the future for LLVM look like?
Okay, for the first question, there are many use cases. First, let's see. You can build your own compiler frontends in Python. You can design your own programming language which targets LLVM. I think it's a great feature to have. Numba does it. It designs a Python frontend for LLVM. And the other benefit is you can create these tools that I have mentioned over here. So some of these can come very handy. For example, those visualization passes. So I have found myself stuck on how this automation is working. Then I have to go to Godbolt or to fire up my own LLVM tools and try to dump those optimization images, control flow graphs, and it gets very messy. So it's very helpful for developing those tools which might help you in day-to-day development. And coming to the future of LLVMlite, the first thing is we want to move it to LLVM 1020 or tip of trunk. Maybe try to pitch it to more projects to use. Right now, I think its only user is Numba, but it has a lot of potential to be used by many projects.
Cool. Thank you very much.
Sure, no problem.